We are continuing our study of related rates. This is day 1 where we are looking at Pythagorean theorem problems. Today we're going to look at a boat problem. Now previously you learned how to work with a ladder problem where a ladder is sliding away from a wall. This is just another variation of a Pythagorean theorem problem where we look at a boat. So Mr. Karcher, who we miss and love, was returning from a day out fishing. His boat was pulled into a dock by a rope attached to the bow of the boat and passing through a pulley on the dock that is 3 meters higher than the bow of the boat. Okay, so if you're not a boater, and I am not, I had trouble the first time envisioning what this was going to look like. So here's the bow of the boat. There's a little pulley system, and there's a rope coming off of there, and there is a dock. Let's say this is the dock. Maybe there's a person standing on the dock who's going to help with this pulley system here. So there is a rope that is going to get attached from the bow of the boat to the dock itself. And we're looking at how quickly that boat approaches the dock. This is my dock over here. And it says the rope is attached to the bow of the boat and passes through a pulley on the dock that is 3 meters higher than the bow of the boat, which means this is a distance that will not change as the boat gets closer and closer to the dock, which means I can refer to this as a constant number, as opposed to the other measurements in this little triangle that's created. As the boat gets closer to the dock, this distance is going to change. It's going to get smaller. So I'm going to call that a variable x. And then as this gets closer, my rope is also going to be changing. It's going to be getting smaller and smaller and smaller. So I'm just going to call that z. So we know our first goal is to draw a diagram. And then let's see if we can come up with an equation to use to relate something on the diagram. Well, we've got 3 sides of a right triangle. That is our good old friend Pythagorean theorem. So x squared plus 3 squared equals z squared. And I've got lots of information to identify, but I like to right away go ahead and differentiate this. So my derivative of x squared would be 2x. Now remember, we're using implicit differentiation. We're differentiating with respect to time. So we're going to include dx dt, which means this is the derivative of x with respect to time. 3 squared is 9, but the derivative of 9 is 0. And on this side, the derivative of z squared is 2z times dz dt. All right, so we've got 4 different variables we're working with. So let's identify what we have and what we're trying to find. So we've already taken care of the 3 meters between the dock and the bow of the boat. The rope is being pulled in at a rate of 2 meters per second. So that is the rate that the rope is changing. That is going to be our dz dt. It is 2 meters per second. And if this is getting pulled in, this is a decreasing distance. So that should be a negative rate. So negative 2 meters per second. How fast was the boat approaching the dock? So they want me to find dx dt. At the moment when the boat was 12 meters from the dock. So when the boat was 12 meters from the dock, that's like my moment in time. So we always make sure we differentiate our equation before we start substituting in any of these rates or measurements. So let's see what we know. We now know that there is a moment in time when x is equal to 12. So I can substitute this 12 in here. I do not know dx dt. That's going to be a variable. On the other side, I do not know z. However, if I'm focusing on a very specific moment in time, and I know this is 12 and this is 3, I can find what z is. So I'm going to leave this blank for right now, but I'm going to come back and I'm going to find what z is. And I also know that dz dt was given to me, so that is negative 2. So we're going to use Pythagorean theorem again. I basically use this Pythagorean theorem once to implicitly differentiate it and generate rates. And I'm going to use it again for a very specific instant in time. And at that instant, they're telling me x is 12. So we've got a 12 right here. So 12 squared plus 9 equals z squared. So that's 144 plus 9. So that's going to be 153. And when I take the square root of both sides, we get plus or minus square root of 153, but we know we're not working with negative distances, so we can just focus on the positive square root of 153. If you're an IB student, you do not need to reduce your radical. You can keep it like that. If you are a Calc Honors student, you can approximate that as a decimal. And if you are either one of those students, you can reduce this. I'm going to go ahead and reduce this. So we can divide square root of 153 by 9. And that leaves me with 17. And the square root of 9 is 3. So we have 3 square root of 17. And I'm going to drop that 3 square root of 17 up here for z. And then we'll clean this up. So we've got 24 dx dt equals, that's negative 4 times 3. So negative 12 square root of 17. I'm going to divide both sides by 24. That leaves me with dx dt equals negative square root of 17 over 2. Let's get a unit on there. So my x unit is in meters. So my numerator's unit is meters. My time unit is in seconds. So this is a meters per second rate. And I would expect this to be negative because the boat is getting closer to the dock, so this is a decreasing distance. And now you've seen 2 different Pythagorean theorem examples, a boat problem and a ladder problem. Thank you so much for listening. Good luck.